Uh, Good evening, Ayush. We are live now, YouTube live. Please go ahead.
Okay. Samriddhi, you can proceed ahead. I have given you the host access.
So, hello everyone. Am I audible?
Yes.
Yes, you're audible.
Thank you so much for confirming. So, good evening, my fellow mates and distinguished guests. It's my privilege to introduce you to our esteemed guest for today, Dr. Prashant Pathak. Dr. Pathak is highly regarded scientist in the field of space, planetary and astronomical sciences and engineering. He holds a PhD from SOKENDAI University, a testament to his dedication to academic excellence and expertise in his field. Dr. Pathak currently serves as an assistant professor in the Department of Space, Planetary and Astronomical Sciences and Engineering at IIT Kanpur, where his work has left an indelible mark. Dr. Pathak's research interests are both extensive and groundbreaking, encompassing the following areas. First, direct imaging and characterization of exoplanets. Second, adaptive optics and wavefront control techniques. This field has advanced our ability to capture clear and precise images of distant objects, pushing the boundaries of observational technology. Third, ground and space based instrumentation. This encompasses developing cutting edge instruments for both ground and space based observatories. His dedication and contribution to the field of space and planetary sciences are evident in his extensive list of publications. Some of his notable works include exoplanets with ELT methods. 1. Estimating the direct imaging exoplanet yield around a star within 6.5 parsecs. Second, constraints on the nearby exoplanet Epsilon in the AB from near deep and mid-infrared imaging limits. Third, imaging low mass planets within Alpha Centauri's habitable zone. Fourth, high accuracy short term precipitable water vapor operational forecast at the Very Large Telescope. Metis high contrast imaging design and expected performance. And the last one, on sky closed loop correction of atmospheric dispersion for high contrast coronagraphy and astrometry. With an impressive career trajectory, Dr. Pathak has gained valuable experience as a postdoc fellow at the University of Liège, Belgium, and as an engineering and technology research fellow at the European Southern Observatory ESO in Germany. His work has not only contributed to our understanding of exoplanets and advanced imaging techniques, but also pushed the boundaries of technological advancements in the astronomy field. We are honored to have you with us today, and we eagerly anticipate his lecture, which promises uh, to be both be enlightening and inspiring. We welcome you, Dr. Professor Prashant, and my fellow co-host Nidhi would continue from here. She is the head of history department at Synapse Society. Nidhi, will you be taking over now?
Yes, thanks, Samriddhi. Good evening, sir. It has been really nice to have you here. So, as your expertise lies in the field of exoplanets and optical instruments, would you like to tell us something about the telescopes and optical instruments that are used in studying these exoplanets, like ground-based telescopes? Am I clear, Samriddhi?
Sorry, it got disconnected. Sorry about that. Can you repeat the question? Sorry.
Yes. So, as your expertise lies in field of exoplanets and optical instruments that are used, would you like to tell us something about the ground-based telescopes?
Sure. So, the field I have been working on throughout my
Sorry, sir, you were not audible. The audio and video lag. Can you
Just give me a second. I'll call him. No issue. There might be a network issue.
Sorry. Now I should be back.
Yeah. You are back. You're back. You're audible.
I don't know, Wi-Fi has been not very stable. It was working fine, but okay. So let me repeat. Hopefully, it stays fine. So I have been working on the exoplanet sciences. So the reason we have like not been able to directly image exoplanets and finding planets outside our own solar system, it's a very kind of it's a decade old. Recently, only we have been able to tell that if planets outside our solar system exist. There has been a theory that, okay, there are planets in our solar system, there should be planets on other systems also. But we only were able to confirm very recently. The reason was that the requirements for imaging or finding exoplanets are very stringent, and you need large telescopes for that, and you need to achieve a high angular resolution. So then only you can image planets around other stars than our own sun.
So, what are the future prospects of this ground-based telescoping technology, and how can it change the world of astronomy?
Sure. So as you can see that, like, okay, telescopes were discovered centuries ago, and over this history, if you see that the size of the telescopes has been increasing. And only very recently, around like 90s, we are able to use adaptive optics. So in general, when you have a telescope, anything larger than maybe 10 to 20 centimeter larger telescope, if you have more bigger than amateur size telescope, so you're limited by atmospheric seeing. And this was observed not just recently, it was always there, like because of the Earth atmosphere. So when Newton used his telescope, he also saw that stars were not stable, they were twinkling, and we see this with the eye also. So atmospheric impacts, like due to refraction of light coming from the stars, the wavefront error gets introduced in the light, and that causes a twinkling or a changing of its shape of the stars. So that limits the how well you can resolve any object when you use ground-based telescope. So people in 1950, there was a scientist, he proposed the idea that you can really compensate for the turbulence of the atmosphere. And because of the technological limitation, it could not be done at that time. And when there was a space war was going on between US and Russia, so US really wanted to image satellites of Russian satellites. So they developed, they had telescopes for army. So they worked on this secretly on this technique called adaptive optics. So what you basically does in a simple way is that whatever the turbulence or through atmosphere, the wavefront aberration or error, you can say, gets introduced in the by the atmosphere. You measure that using a wavefront sensor. So that can be the different kind of wavefront sensor. So basically, you can actually just there are like knife edge test, which was done for like 300 years to estimate the wavefront error in the lens when you manufacture it. So there are other ways you can estimate the wavefront error. So if you can measure how much error is getting introduced through the atmosphere, you can correct it using somehow like changing the shape of the mirror. So you correct and you get back the resolution of the telescope. So this was done secretly by US defense. And in 1990s, Europe scientists were working on this parallelly, and they were able to demonstrate first time the use of adaptive optics techniques on sky for astronomical observation. And since then, after the first demonstration, it was that you can really advance this technology. So around 2000, there were like large telescopes got built, which are like 10-meter class telescopes. So there are like a few of them. So European consortia had 4 large telescope, 10-meter telescope. So these are called VLT, very large telescopes, and they are in Chile. and US and Japanese telescope are in Hawaii. So they have a 10 meters diameter size telescopes, optical telescope, and they had in their telescope program itself, the adaptive optics instrument was built along with the telescope, so that you can achieve the resolution of the theoretical resolution of the telescope. So the first generation of the instruments, you were able to get the quality where is something called Strel ratio. So
I think you lost your voice again. So it will be better
You are
if you
freezed.
turn off the camera and then speak so that everyone can hear. There is a slight network issue at your place, if I'm not wrong. Guys, extremely sorry for the inconvenience. He'll be joining in a while. There is a network issue at his place.
okay, so can you
Yeah.
hear me now?
Yes, sir. We can
Sorry.
hear
Yes,
you.
yes, sir.
Yeah, sorry about that. The Wi-Fi is really unstable, and I don't have a Ethernet connection for my laptop. Uh, so okay, so where I was, Strel ratio is something that when you have a perfect optical system, imaging system, it can be camera or anything, and you achieve the designed performance of that camera, then you call it that you get 100% correction. So Strel ratio is 1. But the first generation of adaptive optic system, they were able to achieve like 20 to 30% level of correction. And with advancement in this field, now we are able to correct for about 90% of the aberration. So which is similar to what you get in the from space telescope. And I believe that in with progress in computation and technology advancement in a fast deformable mirrors, we will be able to in future have a as good as quality as what you get from the space-based telescopes.
So just for clarifying to the viewers, would you like to tell us the difference between ground-based and space-based telescopes?
Sure. So basically the telescopes design way in the design way they are same. The only difference is that you are very much limited by the example like to sorry.
Yeah. You were audible for you were inaudible for a while, so
Okay,
we
yes.
could re-answer the question.
Okay, sorry about that. Okay, so to explain it simply is that you have, for example, you have cell phone camera, right? Then you have a DSLR, and the more like the larger lenses you have, the more light you collect, and the more resolution you're gonna get. So, for example, bird photographers, they have really large lens, and the complexity gets increased the larger aperture size as you increase, right? So when you want to have a large telescope in space, you are limited by size and weight. So, and also the costs gets extremely high. And with a ground-based telescope, you can, for the fraction of the cost, you can have a large telescope. So just to give you example, there's a large telescope coming up in built by Europe, which will be in Chile at Paranal, which is a desert at the Paranal. The cost of that telescope, it's about 39 meter large telescope, and it's about 1 billion euros. And when you see the cost of JWST, it's about 10 billion euros. So, and which is 6 meter in size. So, again, you get good quality when you go to space, but from the ground at the fraction of cost, you can have a large telescope, which will have a better resolution than JWST.
So, are there any challenges or limitations that we face while using ground-based telescopes?
Yes, the biggest challenge is that the atmospheric limitation. Because of the presence of atmosphere, your resolution is very limited. So as I said, with the adaptive optics, you can correct for the limitation imposed by the atmosphere, but also that you can't do wide field. The problem, what happens is that you can only look at a very narrow patch of the sky with the help of adaptive optics. And as you want to increase your field of view, then the complexity increases, and the instrument also, like you need to have way more complex adaptive optic systems to correct for wider field of view. With time, I think that limitation can be overcome.
So, would you like to tell us something about the early universe and the study of cosmic phenomena, and how do these telescopes help us in understanding these things?
Sure. So the telescope, what they do primarily is that with diameter, you can increase the amount of light. It's kind of gathering power, right? So light gathering power. So the larger you telescope you're gonna have, the fainter you're gonna see. And what I mean by fainter is that when you have like an extremely large telescope, so for example, 40 meter in size, in optical, you're gonna get observe galaxies which are born very early at the early time of the universe, and you're gonna see that high redshift galaxies which are very kind of moving very fast. So you're gonna looking back in the time, really, you are looking back. So you're gonna get more information, I would say, with larger telescope. So, and also with large telescopes,
So,
you're gonna see a lot of exoplanets in direct imaging.
so also, if you'd like to tell us something about your study in exoplanets, that will be nice.
Sure. So many of you may know that there are about like 5,000 exoplanets have been confirmed, and majority of them have been imaged using indirect method. Most of them has been imaged using not imaged, confirmed using transit method, which is there's a Kepler Space Telescope which discovered a lot of exoplanets, and very few, about 50 of them, through using direct imaging from ground as well as a JWST from space-based telescope. So the reason, the field I work on is direct imaging. So the advantage of direct imaging over other method is that if you can directly image a planet, then you can take its spectroscopic studies. You can do that, and then you can tell about the gases or atmosphere present in the planet, and you can tell a lot more about us if there is a water or what kind of a temperature of the atmosphere. You can do a lot more studies of the planet and tell if it is habitable or not.
So if a student wants to make a career in this field, what
Yes.
he or she should do?
So depends on what you want to do, right? So there's like two aspects of it. So I mostly work on instrumentation side of this field, and there are a lot of people who work on exoplanets. So there are like a lot of, I know that recently have been a lot more people in India working on exoplanets in NICER and ISA Pune and a few other places, TFR, there are people, and here also at IIT Kanpur, there are a few people working on exoplanets. So obviously, it's very kind of exciting to work in this field. There's a lot of demand in outside. Also, a lot of missions are being planned, space-based. Also, there's a lot of push for ground-based observations in Europe as well as in US. So if you're really interested to kind of work in this field, you can always email me. I'll be happy to answer any questions.
So, what locations are selected for installing large ground-based telescopes? Like, what factors are chosen while installing these things?
Sure. So first of all, like whenever you want to select a site to build a telescope, ground-based telescope, what you do is that you do a large for a really like multi-year survey of the site. So in survey, what includes is that you how many clear nights a year you're gonna get. So you do these studies because you want to build an expensive telescope, and you should be able to use most of the night for observation. That's regarding cloud coverage. The other is the site has to have at a remote location, so you don't have a light pollution. Next is you want to be in a dry site. So generally at the very top of the mountain, the telescopes are situated. So dry, what happens is that you don't want to have a large water vapor or a cloud like relative humidity, because you're going to get a lot of background photons if you look in infrared or mid infrared. So you do this survey, and these surveys are generally done for 5 to 10 years to select a site.
So technically, it takes 15 years to like properly install a ground-based telescope.
Yes, it's also like you've initially, like when these sites were chosen, the one in Chile and Hawaii, people really like went at the top of the mountain, they hiked and they installed these characterization instrument and they characterize it. So now it's well known. So now people build more telescope at the same site. So
Okay.
there is a Indian telescope in Hanalei in Himalayan Chandra, and they also have a proposed dark sky at that site, that there will be no commercial buildings coming up for future. So they want to really preserve that area for observation. So it's in Ladakh. It's called Hanley. So IAI, Indian Institute of Astrophysics, has a few of the telescopes there. So they also did the same, followed the same process when selecting a site, that you have to monitor the sky and measure the seeing. So seeing also is very important. So the way you define a seeing is that you study the atmosphere and see that what's the effect of a atmosphere on the image you form using a telescope. So the way you define a seeing is that there's something called fright parameter. So it's generally called R0. So that what it tells is the coherence length. So for example, generally at a good site, the coherence length is about 15 centimeter. So when you use the statistics of atmosphere, you come up with this parameter that the wavefront of the light is not it doesn't have an error more than a 1 radian. So for example, if you want to, for example, measure the coherence length in any other site in a city, you're gonna have really like about 5 centimeter, maybe if you're good, if you're lucky, then you will get 5 centimeter. What it tells is that if you use any optics or a telescope larger than 5 centimeter, you're gonna have a aberrated image using that. So generally, for amateur telescope, you have like about 5 to 10 centimeters. So you don't really see the effect of turbulence, not very drastically. But if you have large telescope, then you're gonna see the effect of turbulence.
So when you mentioned India, I've also wanted to know that, oh, what are Indian scientists doing in research about exoplanets? Like,
So
yeah, you can continue.
Sure. So there are a lot of people who are using data from they're like in collaboration. They are working to use the data from the Hubble and JWST, and there are people at PRL, Physics Research Laboratory, Ahmedabad. So they have a spectrograph. These are very high resolution spectrograph. So what they do is that they use radial velocity method. I didn't explain. So what you have, for example, you have a two-body system, right? So what happens is that when they are rotating, for example, if we take our solar system, so the planets are rotating around around sun, and then you have a center of mass which is off center from the center of mass of the Earth. So there is a precess. So the planetary bodies presses around that. Sun also presses off center. So there is a change of kind of there's a velocity which changes on the precision of the star. So if you have a high resolution, very high resolution spectrograph, so you can really measure the shift of the change of the star. So this is very similar to Doppler method. So when you have something change of, like something is moving towards you, you hear high frequency, going away, you low frequency. So use a very simple this physics to really measure the position of the star, and then you can tell that if there's an external body around it affecting that position. So the sensitivity you can get with such method is that around 1 to 10 meter per second. So if star is shifting by like around 1 to 10 meter per second in velocity, then you can tell that there is other bodies, and with that you can back calculate the how many what size of the planet is present around its star. And that is used by this physical PRL laboratory. They have a instrument called Paras. So they have discovered some planets around using that technique.
Okay. Sir, how important is it to establish indigenous space telescopes? Would you like to tell us something about it?
It's important. There has been like two space missions. So one was Astrosat, that was mostly like India's first astronomy based satellite, and the second was Aditya L1, which flew like few months back. I think it was September it flew. I don't remember the exact date. So also it's all about technological capability, right? Establishing that you can develop instruments which are space capable to, and also in terms of performance, because these are very high precision instruments. You are talking about like when you have a final wavefront quality you want to see, which is in nanometers of RMS. So with that precision you want to have a imaging system.
So as we have heard that SpaceX always like has some internet satellites. So
Yes.
do these things affect astronomical observations?
Yes, they do affect. So there was actually when I was at ESO, which is a European Southern Observatory. So when the Starlink was initially started launching, there were a lot of people who read about it. So the good thing was that the people from SpaceX were very ready to listen to astronomers. So they came up with something called black coating. So which reduce significantly the amount of reflection you get from the satellite, but still visible after a while. They are a bit faint when they are in orbit, but for radio observations, they do affect significantly.
Also, sir, would you like to explain us about equation of state of heavy mass stars? Like I was reading yesterday that with present technology, we could read and analyze neutron stars to predict different types of equation of states, but we still cannot fix on the right equation of state. So what changes in present technology could help us to move closer in determining them?
I don't have an answer right now. I would have to look on that, unfortunately. So
Someone is asking
yes,
which is the cheapest telescope we can purchase to view space planets.
to view. Sorry.
Someone is asking which is
Yes.
the cheapest telescope we can purchase to view space planets.
Space. Sorry, can you repeat it?
Space planets. A
Space
viewer
planet.
is asking, yes.
Oh, you mean exoplanets?
Yeah.
So I don't think it will be possible to with you really need large telescopes, for example, observatory class telescopes with with amateur telescopes. You can only see terrestrial planets, which is in our own solar system.
Okay. So there are
The reason is that you wouldn't have a sufficient angular resolution to see the planets really far away. You need a lot of a really large diameter to have a sufficient angular resolution. To put it in a simple way is that, for example, our eye is the pupil is about 4 to 6 mm when it depending on how much it is open. So what you can do is that if you have uninterrupted, there's no pollution, and if there's a car is there 100 kilometers away, and you see that the headlights are about like 1.5 meters separated, so you can see you can resolve that if it is a bike or a car, you can see the both headlight about 100 kilometers with the eye. And if you want to put it like, for example, 1000 kilometer, then you have to increase your diameter of the pupil by a factor of 10. So you can do this calculation easily, that how much resolution you get. So you are really limited by the resolution of the telescope.
So there are many students who are very much interested in this field of exoplanets and telescopes.
Yes.
But the issue arises that they don't know how to pursue it. Like without doing PhD, is there a way we can do research on exoplanets and telescopes?
Without doing PhD, you mean?
Yes. Like an internship or anything.
Okay. So it's I don't know about what's the procedure to do internship here, but there are like people who are who work at, for example, TFR or other science institute. They will be happy to have a student working on this. Also, like I was told that here, because of limitation of space, it may not be very easy to have an intern student. So I can tell about here that it will be difficult. There are people working on the exoplanets here. Other institute, I'm sure they will be happy to have a student, for example, TFR and IIA, for example. Some people are there. Nicer also, I know some people.
Okay, sir. So I would be asking you next. So the observable universe, it's 13.6 billion years old. And how do you think we will find galaxies older than that in the observable universe? Like, aren't the telescopes limited by what we see?
Yes, I agree to that. So the more larger the telescope you have, the fainter you're gonna see, right? you have more collecting area. So with a new next generation of telescope, which will be like 3 times more powerful than not 3 times, maybe in angular resolution, yes, but in collecting light collecting area, it's a d square. So for example, you have around 8 to 10 meter, that's the largest optical telescope you have. So that's, you can square it, and with around 30-meter class, you're gonna have more collecting power. So you're gonna see a very kind of faint structure, early universe structure, which we do not know yet what we're gonna see, right? So
So that's very interesting, sir. So next, I would be asking on a little environmental front. So do we need to worry about the environment or protect nature when we build and use ground-based telescopes in remote places?
Sure. So most of the telescopes which I know, the remote, they are really at remote and very dry places. So they do not have any vegetation or any kind of you're not affecting any uh, ecological environment there. So they are really, like, if you look at, they are around 13,000 feet. So there's really barely any oxygen, and you don't have much plant or any living surviving organism, you can say. And the same goes for the, I think, the Hanley also, the one in Ladakh. And the impact wise, what I can say is that once you have a
Sir, you lost your voice. I think the network issue is still prevailing. So if you could reconnect. Let's just wait for a while till he's reconnecting. Okay, till the time sir is coming back, I guess he's reconnecting his Wi-Fi, no use. Till the time he's coming back, you guys can just roll out the questions you want to ask in the chat section. We'll be taking your questions in the last, like in the next few minutes. So whatever questions you have, just roll them out in the chat section. I'm giving the chat section allowance to everyone. Yeah, you can type the question in.
hello.
Yes, sir, you are audible now.
Okay. Sorry, again, it got disconnected.
No problem, sir. With internet issues happens frequently.
No, it's a new building they have. Sure, the department has been opened, and the internet has been not very, especially the Wi-Fi, not been very stable, unfortunately. So, and also the phone network is not very good. So it's just Okay, so
So,
I hope I was able to, I didn't get disconnected, but generally I haven't seen any impact uh, from the telescope construction at remote sites. It has very minimal impact, I would say.
So someone from the audience is asking,
Yes.
how many exoplanets are discovered by Indian scientists?
Okay, that's a question. I know that they're like new, I'm not sure, but they have done a follow-up observation using there's a facility in Aries. There are a few telescopes there. So using those telescopes, they have uh, did multiple observations of same target, and they were able to have a achieved very high signal detection signal. And the same for the telescopes at PRL. They have some telescopes in uh, I forgot near Udaipur. There's a place which has some observatory. So using that facility, they were able to detect already known planets.
So one more from the audience. How
Yes.
has technology such as advanced imaging and data analysis techniques improved
Yes.
the capabilities of ground-based telescopes in recent years?
Oh yes, so that's so when you think of like telescopes, you can put it in a simply like using cell phone, right? So when you think of like 10 years back, the cell phone quality were really shitty. So like you could like just have for like memory, you can take picture. You couldn't get a good quality. But bit with time, you had the sensors got better, and optics got better, and also the image processing, which is really has changed the pictures we take from cell phone, right? And the same goes for images using telescopes, is that there's a lot of uh, advanced processing which is required to get a good quality, especially for exoplanet science cases. So you are limited by a lot of background noise, and other errors are there. So you use a lot of post processing. So these are for example, you use a principal component analysis, if you're aware of it. So, and also there's a recently have been a lot of use of machine learning in this field.
So what is principal component analysis?
So when you have a kind of image, so you can basically break that image into a set of vectors. So basically, it's very similar to put it in a uh, if you have if you know about Fourier transform. So
Yes.
yes, so Fourier transform, you basically if you do Fourier transform, you break into, you have spatial frequencies in Fourier space, right? So in the same way, you take you have an image and you have matrix, and you take a, principal component analysis. So you get vectors and there's a principal component, so which defines that what are the different component of which most of your image consists of. So it's kind of filtering technique, you can say.
Okay. So one more from the audience. Are there any open databases available giving access to data from some satellites and observations?
Okay. So I haven't used Hubble data. So a lot of people use Hubble archive, and when the field emerged like 10 years back, that people kind of got like started that okay, exoplanets, you can find them, they are faint, but if you use clever algorithms to detect planets, then you can find it even using on Hubble data. So they went and digged up the archive of past 10 years, and they were able to find planets using Hubble data, for example. The other is that ESO, European Southern Observatory, which is in Europe, they have a archive which is open. So they generally, after observation is completed, so it goes to the scientist of the consortium, but after a while they put it on archive, and a lot of people use that data to use their own technique to post processing, for example, and find planets they dig up. So it's all about, like, if you come up with a algorithm or clever technique, which for example, if you have machine learning technique which can help you to find which is more sensitive to find planets in data, then you use that, and then people go and dig up the archive and use that to find planets.
So, I'm sorry for the interruption, sir.
That's fine.
Which is better, building space telescope with collab with other space agencies, or building own telescope or collecting the astronomical data? It's a question from the audience.
Yes, so it's also like a kind of a it's a very kind of a answer which is a tricky one. So, for example, I can give you one example which may answer this, and then I can like try to give overview. So, there's something there's I talked about ELT. This is a very large telescope coming up, built by European countries, which is gonna be largest telescope on Earth. So the instruments which were gonna go there are like three instruments. So I worked for 5 years on one of the instrument, which is a METIS. So it's stands for mid infrared imaging and telescopes. It will be imaging and spectrograph. So the way is that for building that instrument, it's very kind of a very large instrument, very expensive. So a lot of member countries and institutes come together to build that instrument. So the expertise comes from different places. So these are very really complex instruments. So these will be fully cryogenic. So what I mean is that the instrument is going to work at around 70 degree Kelvin. So that's about like I forgot, it was a CO2 cooling, but anyway, forget about that. So it's a cryogenic instrument, so it's gonna work at a very cold temperature, and for that you need to have for example, rotators. So you have to kind of find rotators which are capable to work at a very cold temperature. So there's a place called Saclay. It's a CNRS place in France. So they expertise on building such motors which can work at a very cold temperature. So such things, they also developed the instrument for the JWST, the MIRI instrument. It's a mid-infrared. So you use such expertise from different institute to build the best thing you can. And generally, it's very useful. Sometimes when you collaborate, you get the best, right? And
Yes.
when you go on working on developing your own, so it takes time also. It's good to develop on yours, so it's depending on the requirement you do this, right? So sometimes
Yes.
it's useful, and sometimes it's good to have your own thing to do.
So what materials are used in making such things that can handle cold temperatures?
So that's also one thing that you kind of study these things. So there are like optical companies which develop such material, and sometimes it's really hard to obtain such material. So they're like, for example, in infrared, you use calcium fluoride mirrors. Not mirrors, sorry, lenses, which can work at cold temperatures. So, for example, like there are a lot of studies, like for example, what kind of glue you use to put it together, which can work at a cold temperature.
Yes. So talking about lenses, so in ninth standard we had a chapter of convex and concave lenses,
Yes.
which told us about imaging. What type of lenses do these telescopes use?
So generally, you try to avoid lenses in telescope. The reason is that like you only use at a way end when you don't kind of have no option. So the reason is that when you use lenses or any refractive medium, you're gonna have aberrations, right? You study that when you move away from paraxial rays, whatever the calculation you do, it's only good for paraxial. And the best way to put it is that when you have mirror, so when you focus light, for example, mirror, all the light, all the wavelength of light, it's going to be focused at one point, at the focus of using mirror, right? And when you use lens, it will be focused at different focal point,
Different
because
focal points.
each wavelength will have its own corresponding focal. So it's easy to do any optical design using lenses, sorry, mirror. And lenses you avoid. So the best way to put it, example again give, is that when you have larger system, so sports photographer or wildlife photographer, they have really large lenses. So the more bigger lens you have, the more aberration you're going to have. To correct that aberration, you have additional set of lenses to correct for that aberration. So you have really big lenses. So to avoid the same thing, you use mirror.
So does light pollution in any manner affects these observational aspects in
Yes.
ground-based telescopes?
So light pollution is a big problem. So when I was in Hawaii for working at Subaru Telescope, so the way they had like planned the city, obviously the telescope site was a bit far from the city. So all the street lights, they had a fixed kind of a yellow light which doesn't interfere they didn't have white light as a street light. So they had a yellow light lamp designed, and that was used throughout the city, which minimizes the background light you're going to get. Also, the other example I can give is that when there are like some observations when you're doing, you really try to avoid looking very close to moon. So moon is so bright you can't look. So you generally like look away, do the observation. If moon is high, you don't observe uh, in that direction. So that's another example.
Um, Thank you so much, sir, for telling us. So, can you tell us something about the super Earth phenomenon? We have all heard it, but most of us don't understand what it is all about.
So I'm not sure what you mean by super Earth, but the way like the detection exoplanets have been detected so far. So because of the method you use, you are only sensitive to a particular type of exoplanets. So for example, if you use radial velocity method, so if planet is really large enough, then only it can perturb the position of a star. So you are more sensitive to close by and larger super Earth planets. And either you can, and with direct imaging, you can see far away, which are separated large at a good separation from the host star. Those planets only you can see, and they should be big enough to have enough light emitting in direct imaging. So there is a really gap between, for example, having exoplanets which are Jupiter size and also super Earth.
Okay, so how has your experience as a postdoc fellow at University of Leeds in Belgium and as a research fellow at the European Southern Observatory influenced your approach to research and your career trajectory?
Okay, so my first postdoc after my PhD was at European Southern Observatory. So it was I really liked working at that place. The whole reason was that it's a kind of to put it that it's like ISRO. So you have like experts which are like really like work. They know they have been working on the same field for like 20-30 years, and you're really working with them alongside. So they are doing really aligning optics, working with you parallelly, and you learn a lot. And the other part was that there are a lot of projects and you can parallelly get interested in different projects. You can get involved. Okay, I want to do this, I want to contribute in this. So you have a lot of options to choose from, I can say. And that was a good thing about or it was the best place to work, I would say. And at university, generally you have a small group focused on a very particular area of research. So you have expert in that, but then you are limited by option. You work on what the group or the instrument they are working on. So there's like pros and cons, but yeah.
So, what advice would you offer to earlier career scientists who are aspiring to make significant contributions in the field of space and planetary sciences?
So I think this field is like that. I really like working on instrument. The reason is that, like, for example, when I was an undergrad, I liked working on experiments more than theory. So I worked at like Saha Institute for like working gamma ray detection using photomultiplier tube. So that's I found that was a bit limiting for me. I wanted to work on full end-to-end system. So and that I got experience at Pune, one of the astronomical institutes. So it's like instrumentation is something you work on end to end. So you from very basic you develop everything, and it has everything, I would say. So for example, if you really like electronics, you can actually like see how a camera works, how CCD, like how the each pixel value get translated from those analog value to digital, and then these is like you can change the timing, everything at basic calibration, and then you can work on optics. And if you like software, so then you can work on image processing. So yeah, I think this field has everything. So that what's kind of a uh, what I like about this field.
Currently, I am also pursuing a degree in electronics.
Okay, that's
So,
nice.
yeah, so as an electronics undergraduate, what future prospects do I have in this field?
Uh, I think that it's a really like a great as a field you get to kind of a lot of like for example, if you not talk about commercial CCDs or CMOS detectors. So for this you get these arrays from companies which they just kind of bake these arrays which are CCDs, and they have a way to collect it. But you have to do full readout electronics on your own. A lot of places specialize on that. So I know Ayuka, it's a astronomy place in Pune. So they specialize on developing readout electronics for cameras, different type of cameras like visible and also near infrared. So these are FPGAs. So you know a field programmable gate arrays. So you really kind of program these FPGAs and do the circuit design. So that requires like developing and circuit so that you can read out the uh, CCDs.
Okay. Thank you so much, sir. I would now like to give mic to Samriddhi, my co-host.
Okay.
Thanks a lot, sir. Thanks a lot, Nidhi. So now we would be concluding our event, and as we come to the conclusion of today's guest lecture, I want to express my heartfelt gratitude to all of you for joining us and making this event a resounding success. Our deep appreciation goes to our esteemed guest lecturer, Dr. Pathak, for gracing us with his knowledge, expertise, and insights. Dr. Pathak's session has been nothing short of enlightening, providing us with a glimpse into the cutting edge research and innovations in the field of space, planetary, and astronomical sciences. His extensive contributions to the study of exoplanets, adaptive optics, and ground and space based instrumentation have left an indelible mark on our understanding of the universe. We have been privileged to hear about his groundbreaking work as well as the advancements he has made in the development of high precision imaging technologies. Dr. Pathak's dedication to his field and his commitment to pushing the boundaries of what we can observe and discover in the cosmos are truly commendable. And as we are leaving here today, let's take with us the knowledge and inspiration gained from this session. Dr. Prashant Pathak has reminded us of the limitless possibilities that lie in the exploration of our universe and the importance of continued scientific inquiry and innovation. Thank you once again, sir, for sharing your expertise with us. and to our wonderful audience. Your presence and engagement have enriched this event. So let's continue to support and nurture the spirit of scientific curiosity and exploration. We look forward to more enlightening discussions and sessions like this in the future. So, with this, I would be concluding today's meet. Thank you, sir. Thank you, everyone. Uh, so, yes, thanks
Before
again.
Yeah.
ending the meet, sir, if you want to say something for all
No,
the
I would like
students.
to thank you for the opportunity and the kind of I hope I was able to provide some answers, but it was a bit like here and there. I think that they were a bit short, but anyway, and I'm really sorry about the Wi-Fi issues.
It's all
No issues,
right.
sir.
Wi-Fi
Normally
issues,
not
it
available.
happens with everyone, and your answers were truly enlightening, like for us at an introductory level. So, thank you very much for coming today in the session.
Thank you.
Thank you, everyone. Thank you for joining in. Thank you so much, sir. Samrit, you can end the meeting for all.